Now that we have learned about this type of compounds and how they are formed and the type of chemical bonds that they form, we can look into how does ozone decompose in UV light. So when I look at this, right, I need to look at the structure of ozone. So oxygen is in the group 6 of the periodic table. Therefore, it has 6 valence electrons. In a molecule of ozone, we have 3 oxygen atoms. Therefore, we're going to have a total of 18 electrons. So let's look into that. When I look at oxygen, a single oxygen atom is going to have 1, 2, 3, 4, 5, 6 electrons around it. So let's draw our next oxygen atom and our next one. I'm going to use different colors so we can see what happens with the electrons of each of these. So I have 1, 2, 1, 2, 3, 4, 5, and 6. Let's use a different color. 1, 2, 3, 4, 5, and 6. So notice that I on purposely leave or just kind of draw the pairs of electrons towards the side of the symbol that is not facing the next molecule. So I do that on purpose so it's easily to see which bonds are being formed. So let's see. These two guys over here are going to combine, right? And they're going to form a single bond. Obviously, each of these has to be linked at least once. But when you look at it this way, you're going to end up noticing that, hey, I have one singlet over here and I have one singlet over here. Is that really possible? It is not. Otherwise, the molecule will not be stable. So ozone undergoes a little arrangement in order to allow this to happen. So some of the electrons of one of these guys migrates, and they migrate in order to form a more stable structure. So this is the type of movements that we find. So when I look at my oxygen, and oxygen, and oxygen, I'm going to form a double bond in one side of the molecule, and therefore I end up having a structure like this, and then I form a single bond on the other side of the oxygen with the other oxygen. Now this is how I draw the Lewis dot structure for the ozone. We've noticed that what happened is that two of these electrons this electron actually migrated over here, right? And then this middle oxygen started to rearrange electrons in a different way, where I have one electron coming over here and another electron coming over here, so I can form that double bond. And then over here, I'm just going to form that other double bond, that single bond. Now, this double bond can move from one side to the other. So I could end up drawing this molecule saying that the double bond shows on one side of the oxygen with one of the oxygens or with the other oxygen. Now, regardless of how I draw this, each oxygen atom will not have more than 6 electrons around it. When we look at ozone, and its Lewis dot structure, we need to look into how it behaves under the presence of a UV photon. And then what we've learned is that because of this double bond and the single bond and the resonance structure, meaning that the double bond moves from one side to the other, there has to be a high input of energy in order to break these bonds. So the type of radiation needed to break this type of bond is not just any UV ray, but it's actually the one that has a wavelength of less than 320 nanometers. So what does that mean? Whenever we learned about the different types of UV rays, we have that the UVA, the UVB, and the UVC have different wavelengths. UVA has a 320 to 400 nanometers. UVB has 280 to 300 nanometers. And UVC is 200 to 280 nanometers. So which of these is the type of UV rays that interacts with ozone and is absorbed by it? So we're going to say that, and this is 320, sorry. So we say that it's actually going to be these UVB rays are the ones that we're referring to when we think about breaking these bonds in ozone. And this most of UVB is absorbed by ozone in the stratosphere. So whatever is not absorbed, it passes through the atmosphere, and then this UVB damages the outmost layer of the skin. So this is the type of ray that causes sunburn. So ozone is a natural UVB protector for our screen. It absorbs most of this type of radiation. So imagine what our sun exposure would be like if ozone was not in the atmosphere. So now what does it do? So under the presence of these UV rays, the ozone molecule is broken, and one of the connectors is, one of these bonds is broken, and then we're gonna form we're gonna break it, and we're gonna form oxygen, right? That is bonded with another oxygen atom. And then that's gonna end up being or looking like this, right? So we have oxygen 1, 2, 3, 4, 1, 2, 3, 4, and then we have a oxygen atom that is by itself. Now this is so we're pretty much breaking ozone into oxygen gas and an oxygen atom by itself. So what does it do? I mean, what happens next? So oxygen in the upper atmosphere will react with UV photons, and it will break apart, giving some oxygen atoms by themselves, which due to collisions, very fast collisions, will form the ozone. Then we're also going to find that due to more collisions, then we actually get some oxygen back. So it's replenished, right? So we get oxygen molecules, and those oxygen molecules, thanks to the UV rays coming in, form ozone, and then that ozone goes back to be oxygen. So that's a cycle, and it gives a stability to the concentration of ozone in the stratosphere.